This is ECE 343 Signals and Systems. This will be the sixth part of Chapter 4. So last time we took a look at different block realizations of systems described by constant coefficient linear differential equations. We focused our effort on things like direct form 1, direct form 2, and the transposed versions of those structures. We also took a look at some parallel and series realizations. Today we're going to take it a step further. We're going to look at op-amp realization of systems. So we would like to take what is an integral or differential equation and realize it using op-amps. And so to get us started on this, I just want to remind us of a basic behaviors of op-amps. We've shown here in this particular picture, we have an op-amp circuit. And this op-amp circuit is one that is in a real standard negative feedback configuration. So we have an input voltage feeding into some impedance that can be chosen to be a resistor, a capacitor, an inductor, something like that, that feeds into the negative terminal on an op-amp. And then we're going to have a feedback path. The output of the op-amp is our output. It's a voltage. And there's going to be a feedback impedance, I'm calling that Z of F, that runs from that output back to the inverting terminal as well. So negative feedback. We're going to go ahead and in this case tie the non-inverting terminal to ground. A couple reminders of some ideal op-amp characteristics. An ideal op-amp will maintain equality on the negative and positive terminals. So the inverting and non-inverting input terminals on the op-amp are kept at the same voltage. What that means for us here is that negative terminal in this particular case, which I've labeled V minus, right? That guy is going to be a virtual ground because it's going to always be maintained at the same voltage as the positive terminal, the non-inverting terminal, which is hardwired to ground. The second one is that these op-amps are infinite input impedance devices, which really means that the current that is trying to potentially go into either of those input terminals, so I'm going to show that with some little blue arrows here, these input currents trying to go in there, they see infinite input impedance, and that means that they're going to be currents of zero. So we're going to have no current draw through the input sides of this device. So if I want to do a little analysis, I'm going to go ahead and see if I can come up with a transfer function for this op-amp circuit that is set in this basic negative feedback configuration. And the way I'm going to do it is I'm going to start out by just writing the voltage drop across that first feed forward impedance, that Z of S. And so what I see is that I've got my original voltage, that's that X of S, and it's going to cross over that Z of S and hit V minus, which we know to be zero. So our voltage drop in this first case is going to be X minus V0 or X minus 0, right? And we know that that voltage drop, right, is just going to be the current times the impedance. That's the transform domain equivalent to Ohm's law. And I've gone ahead and labeled the current going through that device Z of S, right, that impedance as being I, and the impedance itself I'm calling Z of S. So Ohm's law says that the voltage across that guy is just current times impedance, something along those lines. If I rewrite this, I can express an expression, or I can find an expression for the current I of S, and that's just the input X of S over the impedance Z of S. I can also do the same sort of an idea looking at the voltage drop across that feedback resistor. And so in the same sort of way, the voltage drop across that guy is Y minus V minus, and V minus is zero because of the ideal op-amp characteristics. And then and I take a look at the current that is going through Z of F. If I look at that node V minus, right, all the currents summing into that node have to be zero. I see I sub S approaching from the left. I know it's an infinite input impedance, so the negating terminal on that op-amp is going to have zero current. That means all of IS that's approaching from the left has to go up through that Z of F. That's a negative orientation from the voltage polarity when I say Y minus zero. So I'm going to have a minus sign out here, and then I have I sub S minus what was that input current. But we know that because of the ideal op-amp characteristic of infinite input impedance, that's also zero. And so that current is going to be multiplied by the impedance Z of F to give us that voltage difference, Y, basically. I can rewrite that slightly, and I can just say Y then is, right, minus I times Z of F, but I had gotten an expression earlier, right? That expression earlier was for what is I of S, right? And so I can take that guy and plug it in there, and then I get my final expression, right? That my output variable, right, Y, is going to be equal to, and I have a minus Z of F over Z of S, right? And then that whole thing multiplying by X of S. I further know that when it comes to a linear time invariant continuous system, that if I take a look at its input-output characteristics in the transform domain, we should have y equals h times x. So we can identify the transfer function or the system function for this op-amp in negative feedback configuration as being minus zf over z, right? It's just a ratio of those impedances, the feedback impedance over the feed-forward impedance with a minus sign in there. So we'll just go ahead and identify that, right? The system function, the transfer function for this op-amp, this kind of generalized op-amp circuit is going to be h of s equals minus zf over z. To implement a constant coefficient linear differential equation, which is really what our goal is, right? We looked last time at just some generic block diagrams. We'd like to back that up with some circuits now. We know that we preferred an integral form to a differential form. That's because of noise considerations. Integrators tend to reduce noise. Differentiators tend to amplify it. So we're going to prefer an integral form. So we're going to have to be able to do an integrator. We're going to have to be able to do some sort of scale multiplier, and we're going to have to be able to do some sort of summation. If we can carry out those three operations, we should be able to implement that constant coefficient linear differential equation written as an integral equation. So let's take a look at these three pieces in turn. I'm going to look first at the scale multiplier, then I'm going to look at the integrator, and then I'm going to look at the summator or summation node. The first one then, a scale multiplier. We know that that scale multiplier, right, we're looking at something that has an overall constant gain for all frequencies. So this is a non-frequency dependent gain. We want to have the same gain over all frequencies. And we know that our op-amp circuit that we've been just looking at can have that behavior if that Z and ZF are both resistors. You could also get this constant behavior if you did both of your impedances as being capacitors or both being inductors, but it would be a really poor idea to do it this way, and so we won't consider that. We're just going to look at the simplest, cheapest, and most reliable way, which is just to make that Z and ZF both resistive in nature. So I'm going to be taking a look at implementing this gain factor, right, K, as done through this op-amp circuit. We're having input voltage X generating an output voltage Y going through this op-amp, and I'm just replacing now those generic impedances with purely resistive elements. So I'm going to have a feed-forward resistor R, and I'm going to have a feedback resistor RF. And if I just use my previous analysis, I know that the transfer function for this system is just minus RF over R. Well, RF is a positive real number. R is a positive real number. That ratio is a positive real number. Put a minus sign out in front, and I just get a negative real number. Okay, so that negative real number is going to be multiplied by the input to give me the output. So that is just a gain factor. So I do get some overall gain. This is a perfectly good way of getting a gain, and you could really design this for, at least theoretically, any gain that you wanted, although you would want to watch what your supply voltages were with the op-amp. You wouldn't want to make it too big, otherwise you might rail the op-amp. But we do have a constraint in this particular configuration that the gain is always negative, right? And so if I wanted to do a positive gain, what I might have to do, this isn't terribly efficient, but it's a way of doing it, I might just cascade two of these op-amp circuits, right? Because two negative numbers in cascade would become positive. So we can still get a positive number out of this. It just might take a few more extra parts in there. So we have a way of doing our scale factor block. That's one of three that we need to do our constant coefficient linear integral equations. The next one is the integrator, and we can do an integrator with some gain as well. We can kind of get that gain for free, so we'll go ahead and allow there to be some gain on this. In the Laplace domain, or in the S domain, the frequency domain, we know integration is just 1 by S. If you remember, we did differentiation. When you do the derivation of a Laplace transform on a derivative operator, you get multiplied by S. And when we do integration, we just get a 1 over S, the inverse of that differentiator, so to speak. So an integrator with gain requires that our transfer function, right, have that gain in there, right? But then I'm going to have to divide that by S, right? Because the 1 over S functions as an integrator. So our op-amp circuit, again, we can get that H of S. We know that its transfer function is minus ZF by Z, right? And so if I can just get ZF by Z to take a form of some constant over S, it's going to function as an integrator with gain. There's a couple ways we can easily do that. And so the first way I'm going to look at is if we put a capacitor in the feedback path. So ZF is equal to 1 over CS. That's the impedance of a capacitor. And we let the feed forward component just be resistive. So just put in a value R in there. So my claim is that we can get an integrator with gain, right, by going ahead and having our input output going through this negative feedback configured op-amp, and that I'm going to allow the feedback path to have a capacitor, and I'm going to have the feed forward path have a resistor. We'd already figured out in this general case what is the transfer function, H of S, and we know it's just a ratio of the feedback impedance over the feed forward impedance. So I'm going to get 1 over CS over R, and that gives me a minus, well, there was a minus sign on there, but a minus 1 over RCS in the denominator as well. I've broken out the minus 1 over RC part separate because that is our gain. So we can set our gain by setting the RC product to whatever value, 1 over RC product to whatever value we want. Again, it's a real number and it has to be negative, okay, because both resistors and capacitors have a positive or non-negative resistance or capacitance. So that 1 over RC with a minus sign out front has always got to be negative. And then the 1 over S is what gives us our integration functionality on that. Okay, that is probably the preferred way to carry out an integrator, at least with this kind of op-amp configuration, but I think it's informative to look at some other ways as well. And so there is a less preferred way. We can swap our components out here where I get that 1 over S behavior by putting in an inductor in the feed forward path and I let the feedback path be purely resistive. So if I look at ZF as being a resistor, right? Its impedance is R, and I look at the feed forward component being an inductor that has an impedance LS, and I plug that into my H of S, and I know H of S is ZF, right? Over the feed forward piece, Z. So that's going to be an R over LS, and then a minus sign up front. The 1 over S part again is going to give me the integration behavior of the overall circuit. And now my gain is slightly different. Instead of being minus 1 over RC, it's minus R by L. Again, this has to be a negative number, and it is real. So we can carry out integration, and we can carry out integration with some gain, but the gain is always going to be negative. If I needed to do a positive integral, right, I would have to cascade maybe an integrator with a gain element, and the two negatives there would make it overall positive, something along those lines. We will do an example of this shortly. The summer, again, can also be done with individual gains, and I'll go ahead and derive it that way. This is just a superposition of the scale multipliers. We know that a summation, and especially if they were going to each have individual gains, right, has no frequency-dependent behavior. We want to be able to add up signals regardless of what is their frequency. We don't want any kind of frequency-varying behavior when we either sum or scale, and summing is really just a superposition of that scale multiplier. So I'm going to give a little bit more generic diagram of what I mean by a summing piece. I'm going to have inputs x1 through xn, so I could potentially have quite a few. This is actually an interesting advantage of an analog implementation here. Unlike computers, things like an op-amp can simultaneously add any number of signals, right? I could have 100 inputs all feeding into the inverting terminal on this op-amp, and this op-amp circuit would be able to add all 100 of those in a single step. There's no need to like add x1 to x2 and then add to that x3 and then add to that x4. This analog solution adds them all together instantaneously, and at least with ideal characteristics would do so without delay. So we have our inputs x1 all the way through xn. Each of them is going to have their own gain. So I might have k1 through kn, something along those lines. And then I'm just showing this as a kind of a triangular block. This is similar to what's done in the book. And our output y then is just a sum of each of those inputs, each multiplied by their respective gains. The way I can do this is I can think about how would I get a scale factor kx1, for example. So if I just look at that term kx1, that's like a single scale factor, scale multiplier circuit. How do we do that? You have some feedback resistor, right? And you have some feed forward resistor with x1 feeding as the input. So those things that I circled there in blue would reflect, right? If I put no other input in there, that would reflect a circuit that would output y of s equaling minus rf over r1. So minus rf over r1 would be the constant k1, and that would multiply the input signal there x1. Well, as I add in more and more and more inputs all the way through xn, and it has its own resistor in there, all these currents that come in here, right? All these currents come in here, join at that single node. And we know how currents hit a node. Currents have to sum together, right? All the currents going into a node sum together. So every single one of those input currents that comes together in that node sums together to make a final current that goes through that feedback resistor. That's how we get the summing action, because we know that currents going into a combined node, right? Those currents sum up. That's a Kirchhoff current law, basically. So if I go ahead and do the circuit analysis on this guy, I see that the output y, right, is just a sum over all those inputs, x1 all the way through x of n, each multiplied by their own individual gain factor. I could call those Ki, where I is going from 1 to n, and it's just the ratio of the feedback resistor to the feed forward resistor for the particular input, and then each one of those gains weight their own particular input. If I take a look at those guys, really that just says this equation over here. The output is a sum of a bunch of inputs, each individually multiplied by their own gains. As before, because we're in a negative feedback configured op amp, the gains are negative and they're real. Between these three different components, using the scale multiplier, using the integrator, and then using the adding circuit, and the integrator and adding circuit can be done with gains, we can realize constant coefficient linear differential, probably written as an integral equation. It is somewhat a brute force approach, okay? It's rarely efficient, but it gets the job done. I think there are entire classes, full-length textbooks that talk about efficient electronic realizations of these transfer functions. We're just starting the process. We're doing something that's relatively simple to work through, and probably will not be 100% efficient, but it does give us a solution that we could realize using actual components and that we could wire up in the lab. Let's go ahead and demonstrate these three together for a particular example. I'm going to pick a pretty simple example, and we would like to go ahead and realize a transfer function. So I've got a transfer function here of interest. It's just going to be 5 over s plus 3, and I'd like to realize that with op amps. The first thing I notice is that a transfer function, right, is just the ratio of output to input. That was one of the definitions we had in a previous lecture about this transfer function. If I cross multiply here, right, so if I go ahead and take this s plus 3 and multiply so it goes against that y, and I take this 5 and this x and I multiply those guys together, we can get those on each a separate side of the equation. And if I do that, what I find is that, let's take the first one here, s plus 3, coming over here and multiplying the y by the ys, that's going to give me an sys plus 3ys, right? So that's one side of the equation. Take the x of s to the other side, and I'm going to get 5x of s. So this transfer function, when related in terms of the input and output, can give us an equation that relates output to input. So sy of s plus 3ys equals 5x of s. I'm going to invert Laplace transform that, because what I really would like to have is I'd like to have my integral equation so I know what it is that I'm trying to realize. And so I know by invert transforming that, s times any variable is just the derivative of that variable. So I'm going to get y dot, and then I have 3y, and I have that whole thing being equal to 5x, something along those lines. I don't want to do a derivative form of my differential equation. I'd like to do the integral form of that equation. So I'm going to integrate that one once, because it was a first order differential equation. If I integrate once, I'll get a first order integral equation. So integrate a derivative, I just get back the signal of interest. Take 3y and integrate it, I'm going to get 3 integral y, right? Take 5x and integrate it, I'm going to get 5 integral x. It does get to be just a little bit annoying to carry out the full detailed limits of these integrals going minus infinity to t of y of some dummy variable. I called it tau here. So I'm going to do some simplicity here. I'm just going to do that probably more mathematically correct form of minus infinity to t y tau d tau, that integral, and just show it as integral y. We know what that means, and then I don't have to be spending too much time on notation that's unnecessary for the realization. Okay, so what am I going to do? I'm going to go ahead and take this expression, right, and I'm going to solve it for y, and I'm going to solve it for y such that that expression shows me explicitly things like scale multiplication, integration, and summation, all with the constraint that they have to have negative gains associated with them. So I'm going to solve y of t. So I'm going to put y of t over here on the left. On the right-hand side, I see that I had 5 integral x, something along those lines. But I know when I integrate, I'm going to get a negative sign. So what I'm going to do first is I'm going to integrate it, and I know I get a minus integral x. And then I need to get that gain 5 in there. I could have put that with the integrator. I choose to do it outside of the integrator in this particular case. So I'm going to take a gain of minus 5 onto that, and I'm going to make that as part of my summing node. Now, because each of those two terms, each of those two pieces are constrained to have negative gains, when I do it together, right, I'm going to get the desired plus 5 that I had in my original equation. Now, when it comes to this last term, the 3 integral y, right, I need to bring that over to the other side. That's going to give it a minus sign, so I'm going to be looking for minus 3 integral y. Let's start with just the integration. I'm going to get an integral, but integrators are required to have negative gains, so I'm going to have a minus integral y. I could sum that in. I could think about trying to sum it in. I could sum it in with my other component, my integral x. But if I did that directly, it would have the wrong sign because x and this y, both integrated pieces, have different signs, right? We had 5 integral x, but we have minus 3 integral y. So I'm going to have to throw in another stage in here to negate that integral y. So that's going to make it first minus integral y, then through a gain stage of minus 1. That's going to give me integral y. And then the last piece, I'm going to do that minus 3 gain as part of my summing. That would give me the minus 3 integral y that I desire. So let me go ahead and think about how I can realize this, all right, with those three components: scale, multiplier, integrator, and then summer. And they have gains, and we know that every single one of those is constrained to have an overall negative gain. I'm going to go ahead and show the 3 different parts, the 3 different building blocks here, and then we're going to build it up with these 3 building blocks. The first one, a scale multiplier, was just those 2 resistors and the negative op amp, negative feedback op amp configuration. The next one was the integrator. I'm going to do that with a capacitor and resistor as shown there. So the first one, right, this is the scale factor, right? This guy is my integrator, and this guy here is my summer. It's going to sum up 2 pieces. We had an expression for y, and we saw that y was minus integral x, then carried through with a minus 5, getting summed to a minus integral y made positive, and then summed in with a gain of 3. So I've labeled each piece that's in a parenthesis with the part that I need to do it, right? So there's 2 pieces in there that involve integrations. I've labeled both of those 2. So I had minus integral x, that's going to have to go through an integrator-like circuit. I have minus integral y, that's going to have to go through an integrator circuit. I have something that is going to require an overall sign change or a gain factor of minus 1. I could do that with that scale factor, so circuit number 1. And then the last piece, when I'm going to sum these 2 pieces together, I'm going to hook those 2 together, so that's why the line goes between them, and I'm going to use that summing circuit to be able to bring these 2 pieces together, each with gain. Now, I recognize that there's different ways of realizing this. You could put that gain associated with other parts. I could have done the integrators with the gain. I think it's informative to look at how to do gains when you're summing in, because there's some simple rules there that help you when you're doing that summing operation plus wanting to get the gain. So let's go ahead and work our way on that. So the way I'm going to start this is I'm going to think about what it is that I'm trying to do. I'm looking first as I work my way left to right across there. I see that I'm going to need an integral x. And so I'm going to go ahead and do a little cleanup up here. I'm going to make it so that I can grab each one of these, and I'm going to go ahead and grab one of these integrator circuits. So let me go ahead and grab that guy. I'm going to copy it out, and I'm going to put it over here and just place it down. So I'm going to go ahead and grab my integrator. We'll worry about component values here in a moment. And what I know is that I'm going to be feeding in x on this guy. And what comes out of this is going to hopefully be minus integral x. I do think it's worthwhile when you're drawing out these circuits to go ahead and label the output of each op amp so that you can follow along as to what is being done. We know that that integrator output, right, is going to be working together with that summing node, right? So I'm going to have to go through a summing node. So the output of this first integrator is going to be going into a summing circuit, which I'm going to later combine with some of those output terms. So let me go ahead and grab that circuit number 3. So I'm going to go ahead and grab this guy. I'm going to go ahead and make a copy of that guy. I'm going to come down here and I'm going to paste it in. And what I should be able to do is I should just be able to hook that straight up, at least reasonably close, so that that looks like they're connected, something like that. Maybe if I was going to be a little bit, careful, I'm just going to move this guy a little tiny bit. If I can get it to grab, I'm going to move this guy just a little bit closer so we know exactly where that guy is associated with. So I have x coming into the first op amp, out comes negative integral x, and I see that going into this pair of resistors, right? So a summing kind of node through this next op amp. So at least part of what comes out of here should be some sum. I'm going to label this afterwards once I get the resistor values necessary to get the appropriate gain, minus 5 in this particular case. When I come out of that summing op amp, I should be getting y. So I do know that if I just go ahead and I continue this guy on, right, and maybe I'll just pull it up here a little bit and let it dangle out here, right, what comes out of that summing node should be my output y, something along those lines. Once I have that y, I know that I need to get an integral of it because that's part of what I need to feed back into that summing node. So I'm going to come back here and grab again my integrator circuit. I'm going to go ahead and make a copy of that guy, and I'm going to go ahead and place it in here, something along these lines. So let's go ahead and see if we can get this guy in there, and I'm going to put that in, and I'm going to move that output guy just a little bit so that we can make some space. Try to, if I can get my iPad to grab it. There we go. So output of this guy is going to be y, something like that. Because the input here, right, was y, this last integrator circuit, or this last op amp that I just put in, what we know is going to come out of this, as long as I get my resistor capacitor values right, is I should get minus integral y. So I'm going to go ahead and label that one as well. That minus integral y needs to go through a gain factor of -1. So I'm going to go ahead and grab my gain circuit. So here's my gain circuit, right? Going to go ahead and copy that guy out, and we're going to place it in and allow that one to be hooked up to that part that I just got my negative integral y on. So I have something like that. That was the input into this guy. As long as I get my gains right? Something so that I get a gain of 1. That means the feedback resistor is going to have to match the feed forward resistor. Let's go ahead and do that. Let's pick some realistic component values. If I go ahead and put in here something like a 10 kilo ohm resistor, and I also put a 10 kilo ohm resistor here, RF over R is 1, and we know it has a minus sign. So what's going to come out of this guy? It's going to be minus of a minus integral y. That's just going to be integral y. So I have integral y right now on it, something along those lines. I now need to take this guy and I need to run that output as part of the input to my summing node. So I'm almost done here. And so I'm going to go ahead in this particular case and just see if I can go ahead and grab this guy. That was integral y, right? And it's going to come in here and feed into my summing node on the other side. I do have a few other component values to choose. Let's take care of the integrators. These were going to be integrators with a gain of 1, right? We know that the overall transfer function for this integrator using a feedback capacitor and a feed forward resistor was -1 over RC, and that means that I need an RC value equaling to 1. Let me go ahead and do that. Since I have a minus integral, right, I need RC equaling to 1. That's going to give me my overall gain, right, of -1 in there, something along those lines. I need to pick stuff that is practical. I think when it comes down to circuits that involve capacitors and resistors, the most difficult thing to find is a good capacitor. Resistors are much more available and over a wider range than capacitors, so I'm going to go ahead and choose a highly available or a very common type of capacitor. I'll just pick something like a 10 microfarad. So let me go ahead and pick a 10 microfarad. If I have a 10 microfarad, the resistor I need so that the RC product is equal to 1 is going to be 100 kilo ohms. So that tells me this guy over here is going to be 100K. I have a 100K kilo ohm, so 100 kilo ohm resistor on the feed forward and a 10 microfarad in the feedback capacitor. That will give me an overall gain factor of 1, and because it's in a negative feedback configuration, I'm going to have -1 and integrated, so minus integral y. It was the same thing or the same story for x, so I'm going to need, or I could use the same component values. I could put 10 microfarads over there, and I could put a 100 kilo ohm resistor in the feed forward path. So at this point, I'm doing pretty good, right? I have some circuit that should give me out a y. I take that y and I integrate it. That gives me minus integral y. I negate it basically through a gain of -1. That gives me integral y. And then I'm adding to that minus integral x. And we're doing it in a way that we are trying to get individual gains in that summing operation. So the x path needs a gain of 5, and the y path, or the y path, the feedback path, needs a gain of -3. Here's a real simple way of trying to figure out these gains, or at least the resistor values to give us these kind of gains. I need a gain here of 5 and a gain of 3. The minus signs come out automatically because it's in a negative feedback configuration. So I'm just going to take all the gains that we need. This works even beyond just 2 inputs. It could work with however many. However many inputs are going into that summing node, look at all of their gains and multiply the numbers together. So here I'm going to have 5 times 3, that's 15. Make it a practical value. So I'm going to call it 15K, right? 15K, something along those lines. Now, basically, if I want the resistor value for any one of the other inputs, I take all of the gains that are not the one that I'm interested in, multiply them together, and use that as a resistor value. So let's take this first path. This first path I'm trying to find for my x, right? I'm trying to find the resistor value for that x path. that resistor value for the X path, right, is needing to have a gain of 5. So I've got that 5 in there. And I said take all of the ones that are not that 5. In this case, there's only one that's not 5. That's that 3. So I'm going to take that 3. If there had been more, I would have multiplied all them together, and I would get a number. So in this case, I just get 3. And I'm going to take that 3 and give it the same kind of practical factor. So I made the other one 15 times 1,000 to give me kiloohms. I'm going to take this 3 and I'm going to multiply it by 1,000. That's going to give me a 3K. So I'm going to put over here a 3K. Okay. I'm going to do the same thing for the Y. The Y, right, needs a value of 3 on there. Look at all the other gains besides that 3. There's only one. There's 5. Multiply them all together because there's only one. I'm going to take the 5. And because I made it a practical value, I'm going to scale it by the same thing I did all the other resistors. So multiply it by 1,000. I'm going to get a 5K resistor. So I have 5K in here. So if I really wanted to verify now what was going through here, remember that we can use superposition, right? So each one of these paths from each one of the two inputs to the summing node, right? They're going through a feed-forward resistor and they all share the same common feedback resistor. So let's go ahead and handle maybe the input X first. So I have an input X here, right? It becomes a minus integral X going through that integral circuit, right? And then it hits this 3K ohm resistor, right? Going into the negative terminal on this op amp, and then it goes up through that 15K feedback resistor. What's the overall gain here? The gain is minus RF over R. Okay, RF here is 15, the R is 3, so 15K over 3K is 5K. So not 5K, 5. So I'm going to have 5, and then it's negated. So I'm going to have minus 5 times minus integral X. That is going to be 5 integral X. That was just for this path here that came down, and did this sort of stuff. I can do the same sort of stuff when I look at the other guy. So I had integral Y sitting over here, and it's going to be coming along this path, right? And it's, again, through superposition. We can look at this as just a simple scaling operation. And we know that the gain it goes through is going to be RF over R. RF here is 15K. The feed forward is 5K in this case. So 15K over 5K gives me 3. And because they're tied together at the input node, they sum, right? So I'm going to get a plus. Well, it wouldn't be plus because I had a plus integral going in, and all gains through these op amps are negative. So I'm going to have integral Y, right, with a minus 3 gain. So I should get out of here minus 3 integral Y. And now I've got everything I need to get my final thing because I know that this is my result. I have Y being equal to, let's go ahead and make this kind of the regular text color, so we'll go ahead and do this black. So y of t is equal to, and I have 5 integral x, right, minus 3 integral y. And if we go back to what we originally wanted, right, we had y, and I'll do that here, y, right, is equal to 5 integral x, right, and there was a 3 integral y, but brought over to the other side would be a minus, so a minus 3 integral y, which is exactly what we get here. So just a very simple set of operations. Same sort of idea every single time. If you have a differential equation, convert it to integral equation, and break it up so that you can identify integration, scaling, and summing all with that constraint of having a negative sign on it, and then just start laying down your block pieces and determine components as you go along. To finish out this lecture, I'd like to skip topics now, or switch topics. We're getting towards the end of chapter 3 or 4. We're getting towards the end of this Laplace Transform chapter, and the particular one we're going to start looking at now, and we'll spend at least this part of the lecture and at least one more on it, is this idea of what is called frequency response. What I can say is that frequency response is one of the most useful and important topics that we're going to discuss in this class. It is something that really lays a foundation for so many follow-on classes. It gives us so much intuition about system behaviors. It is so useful in understanding and designing and working with systems. So it's really something that we want to understand with full clarity. Here's what we've seen before. We know that when we put an everlasting exponential e to the st into a linear time invariant continuous system, it comes out as exactly the same everlasting exponential, so the shape stays the same, and it just gets multiplied by a complex constant. This was one way, or one of the motivations, or one of the ideas that we had for this system function, or this transfer function h of s. H of s is a frequency-dependent gain, if you will. It has both magnitude and phase, that tells us how an everlasting exponential, right, gets modified going through the system. We can't change the shape, but we can change the gain in the phase. I'm going to simplify this just a little bit. For the most part, we are going to be dealing with real systems, and so this Complex exponential can be a little awkward. It might be easier. You certainly did this in circuits. You talked about sinusoidal steady state behavior. That's really what we're working for here too. So I'm going to go ahead and look at a sinusoid, something like cosine omega t. So this is a real sinusoid of frequency omega, and we're going to apply this guy to our system as well. Through Euler's, I know cosine can be broken up into two exponentials. So I get a half e to the j omega t plus a half e to the minus j omega t. Because it's a linear system, a sum of inputs will just give me, on the output side, a sum of the outputs to each one of those inputs. So the first one in there, right, if I take a look at this first guy, I have a half e to the j omega t. E to the j omega t has to come out as e to the j omega t. That scale factor of a half stays the same. And then what happens? It gets modified by the transfer function, h, right, evaluated at the frequency. The frequency here, s, right, is just j omega. It's on that omega axis. So I'm going to give it h of j omega. I do the same thing for the second term. 1/2, right, e to the minus j omega t comes out as minus 1/2 e to the minus j omega t, modified by that complex constant of the frequency that was put in, so h of minus j omega in this case. Okay, we could probably clean this guy up a bit, and so we will do that. If a system is real, and remember an easy way to tell if a system is real, to look at the original differential equation if it's in standard form. If all the coefficients are real, then it's going to be a real system, right? If a system is real, and this is something we'll prove in detail later when we do some Fourier analysis, then h of j omega is just going to be h star of minus j omega. This is not difficult to prove, but basically it's saying that this thing, h of j omega, has complex conjugate symmetry in it. Once we know that, then we can take this first piece. I'm just going to leave it alone. That's the same piece here. Just copied it over. This, right, and this, we know h of minus j omega is just equal to h star of j omega. And 1/2 e to the minus j omega t is just e to the j omega t complex conjugated. So this whole thing right here can be represented as 1/2 e to the j omega t h j omega complex conjugated. The conjugate here acting on this guy gives me the minus j omega, that's this piece, right? The star acting on h of j omega, because it was a real system, gives me the h of minus j omega. So I've just rewritten this in a little bit different form. I'm saying that cosine omega t comes out and gives me a couple components. It's a first term plus the conjugate of that first term. Well, we know something about adding a complex anything with its conjugate. When you add something to its conjugate, you just get you get twice the real part. If I use that 1/2 and factor that out as well, I'm just going to get the real part, right? The half will cancel with the 2 that would normally come out of that. So this expression on this first line, 1/2 e to the j omega t h of omega, plus the conjugate of that guy can be simplified as the real part of h j omega e to the j omega t. Okay, what do I know about this h of j omega? We're going to get to a very nice result. We're going through the full proof on this, but really once you see the end result, it's what we would expect, and you won't have to go through this proof again. So what is h of j omega? It's a complex function of frequency omega. I can write any complex quantity, right, in its polar form. So I can take the magnitude of that guy, right, and I can take it times e to the j of its phase. I didn't write that explicitly here. Maybe that would be worthwhile here. So I can write, right, h of j omega. H of j omega, if I was going to write that in a slightly different way, it is magnitude h of j omega, right, times e to the j angle of h j omega. And I ran out of space there. But that's just polar form of that guy, okay? So if I take that guy and I multiply by e of j omega, I really should have put in another step here. So let's throw in the other step. We're looking at the real part of what? We're going to have magnitude h of j omega, and then I'm going to have e to the angle h of j omega times e to the j omega t. I can combine those two together because they both share the same base. So that's going to be e to the j, and I'm going to have omega t plus angle h of j omega. Something like that, and finish this guy out. Okay, so what's the real part of that? Real part of this guy, the magnitude of h j omega is a real quantity. If you have something real multiplying another thing, you can pull that real part outside of that real operator. So I should just be able to get that h of j omega magnitude pulled out. This guy right here, right, is just a real quantity. It's going to get pulled outside. It's not affected by that real operator. The real operator is stripping away all the imaginary stuff. What is an e, the remaining part, right? What is an e to the j anything, right? We're going to get a cosine of that stuff plus j sine of that stuff. And if I'm looking at just the real part of that, right, we ignore the j sine stuff and we just get a cosine. So I'm going to get cosine of what is the argument. I'm going to get omega t plus angle h of j omega. So this is really a neat and gorgeous result, okay? What do we get out of this? We get this idea, right, that if I put a sinusoid input into my linear time invariant system, I get the same sinusoid out, cosine omega t, right? But it is modified in amplitude by the absolute value or the magnitude of hj omega, and its phase gets adjusted by the angle of hj omega. In both cases, h of j omega tells us, right, how this real sinusoid gets modified. It's a sinusoid in, cosine omega t, becoming the same sinusoid out, cosine omega t, modified in magnitude and phase. We are going to define h of j omega as the system frequency response. It tells us this complex factor, right, this gain and phase information about how a sinusoid in steady state goes through the system. What's the response to that sinusoid going through the system? We already had said this thing before that there's a polar form to this. H of j omega is magnitude h of j omega e to the j angle of h j omega. We're going to call that magnitude part, the stuff that was multiplying out in front, right? This part out here out front, that magnitude part is going to be something that we're going to call magnitude response. What is the magnitude response? It just tells us the system gain is a function of input frequency. Systems can have frequency dependent gains. We see that like with integrators or differentiators. We see it with anything that has an S in it. So these systems can have a magnitude that changes as a function of frequency. In fact, think about a low pass filter. That's clear that it has a gain as a function of frequency. A low pass filter has a gain near 1 for low frequencies and a gain of 0 for high frequencies, right? So that gain changes as a function of frequency. Magnitude h of j omega tells us that gain. If we plot magnitude h of j omega, we're going to get a snapshot of the frequency selectivity characteristics of this system. Tells us a lot of information. So this magnitude response, it tells us the system gain is a function of frequency. The angle of hj omega tells us the phase response, and we call it the phase response. It tells us how the system offsets the phase of an input sinusoid to create an output sinusoid, same frequency, right? Just shifted in phase. We saw that back up here as well, right? We saw that by saying, hey, that cosine comes through. It got modified in magnitude by the magnitude response, but it also got a phase shift based on that phase response. So h of j omega, the complex quantity, is what we are going to define as frequency response. We can write frequency response because it's a complex function of omega. That makes it kind of hard to plot as a function of the independent variable omega. We can instead write it in polar form as the magnitude response e to the j angle response. Same information. So if you know magnitude and phase response, you know frequency response, right? If I plot magnitude response, now that's a real function of frequency omega. And then same thing with the phase response. That is a real function of frequency omega. We can plot those two graphs and have complete information about the overall frequency response. And together, these tell us how a sinusoid goes through a system, right? It tells us exactly how that sinusoid goes through the system. Let's do a quick example in here. This will finish out the lecture. In the next lecture, we'll continue doing more examples of how we can use frequency response, how we can compute it, how we can look at it, and maybe some ways that we can find it through pole zero information. That will be another nice topic to look at. So in this particular example, I'm going to go ahead and do the frequency response of some system. This h of s is going to be a rational function, and I've just written it in factored form as 1 over s plus 1,000 times s plus 1/10,000th, right? 0.0001. And we'd like to know what the response of that system is to the everlasting sinusoid cosine t. Because this system is a linear time invariant continuous system, we already know that was the result back up here, right? This result back up here, that a cosine in is going to come out as that same cosine output, right? Cosine in gives me cosine out, same frequency, right? It's just going to get modified in magnitude and phase. So I need to know the frequency response information of this system for the frequency of input to the system. In this particular case, if you look at the omega here, we have an omega equaling 1. It's an implied 1, right? So this cosine has an input frequency of omega equaling 1 rad per second. If I want to know how cosine 1t, right, this 1 rad per second cosine goes through the system, I need to look at the frequency response, the system function, right, evaluated at s equals j omega. If you look on the omega axis in the s-plane, this is just where sinusoids live. So h of j1, right, is where the 1 rad per second sinusoid information resides. So let's go ahead and look at h of j1. What does that involve? It requires us to just take that s value, right? Go ahead and look at h of s, right? And we're going to let s equals j omega, or in this case, j1, because j1 is the frequency of interest. If I do that, I'm going to get j plus 1,000, j plus 0.00. I've got something wrong in there. I think I've got one too many zeros in this one. I must have miscopied my notes. Let's go ahead and fix that. So it looks like it was 1,000th, not 1/10,000th, at least the way I did it for the rest of the part. Let's go ahead and keep it that way. So we'll fix that at this point. So my transfer function s plus 1,000 and s plus 1,000th, so 0.001. Go ahead and put in hj1. We're going to get j plus 1,000, right? And j plus 0.001. This turns out to be something you could plug into MATLAB. You could get an exact value here, but let's just do a quick kind of back of the napkin approximation. J compared to 1,000 is tiny. J is small compared to 1,000. So if I looked at that in polar form, right? If I looked at that in the s-plane, right? I would go 1,000 units over here on the horizontal axis, and I would only go 1 unit up on the vertical axis. That's essentially a vector that is 1,000 pointing off to the right. So I'm going to approximate this guy, just because 1,000 is so much bigger than j. I'm going to approximate that guy as 1,000. Okay. In the same sort of way, if I look at this other one, j plus 1,000th, right? Now, if I looked at that guy in the complex plane, I'd go up here all the way to a j, and then I would only move over 1/1000th of a distance over there. That essentially still points up, straight up at the same location essentially as j. So this thing is approximately j. I'm not perfect, but it's really dang close. If you don't believe it, just go ahead and put into your calculator the quantity 1 over j plus 1,000 times j plus 1,000th, and you'll see that it comes out really, really close to this 1 over j 1,000. Go ahead and write this in polar form. I get 1/1000th, and I get e to the minus j pi by 2. So what can I find from this? This 1 by 1,000 is the magnitude, right? The minus pi by 2 is the phase, right? And so cosine t comes through as cosine t. It gets modified in magnitude by the magnitude response, right? And it gets adjusted in phase by the phase component using that frequency that matches the input frequency. So cosine t comes out coming as a cosine t again, but it's 1/1000th as big as it went in at, right? So this thing is severely attenuated. This system is absolutely making that 1 rad per second signal much, much smaller. And it does impart a little bit of a phase change. It puts in about a 90-degree phase change. The steady state response, right? That is what this thing is. It's a steady state response. We could also use this to tell us what the steady state response is to something like a causal exponential. Cosine t ut in the steady state, after all the transients have died down, as long as I have a stable system, will give us exactly the same piece. The book talks about this a little bit more. We can deal more with this in the recitation if you want. If you want the steady state response to a causal component, you can just ignore that u of t and go ahead and figure out the response to this. The u of t will cause some transients. As long as the system is stable, we know transient behaviors decay. They'll eventually go down to 0, and then you're just talking the output in response to a cosine. So whether it's cosine t or a causal cosine, in the steady state, you can all get it with this everlasting sinusoidal kind of behavior using the concepts of frequency response, magnitude, and phase response. You could, if you wanted to, try to get the transient component for this one. If you were going to solve this in its exact way, what would we do? Maybe I would Laplace transform my input, right? Multiply it by the transfer function, because we can multiply in a transform domain expression. That saves us a convolution. And then I could invert transform it. So if you really wanted to see all the terms in there, you could do it this way. And what you would find out is you would get this piece, and then you would get some other pieces that have like some decaying exponential components. So if you waited long enough, those guys would no longer be important and you'd just be left with this. I would make the comment that you cannot take this approach of taking the Laplace transform of an everlasting cosine times h of s and inverse transform it to figure out the the response to an everlasting exponential. Why not? Why doesn't that work? Because cosine, something that goes on forever, is not Laplace transformable. It has no region of convergence. It's weird, right? So we could show that an everlasting exponential e to the st comes through as e to the st times h of s. We did that through a convolution argument. We did the same sort of thing just a little bit ago by breaking it up with Eulers to show that cosine omega t comes through as, you got the magnitude response of h, and then we have a cosine omega t plus the angle, that sort of stuff. Again, a time domain solution. You can't get it through this transform domain because neither cosine omega t nor e to the st is Laplace transformable, the everlasting versions on these. To end the lecture, I just would like to make the comment, you'll need this for the homework, that you can easily generate plots of the magnitude and phase response using MATLAB. It's super, super easy. Let's just do it for the previous example. I'm going to start out by setting up the transfer function in MATLAB. So I'm going to let h be defined using an anonymous function. So use at parenthesis s, close out the parenthesis, and then just write out the expression. Because you might put in vector values of s, I'm going to use element by element type operation. So I'm going to do a one dot divide, so an element by element division of s plus 1,000 dot times s plus 1,000th, right? I've now got something that defines as an anonymous function, this transfer function h. I'm going to go ahead and set up some frequency variable. For this particular case, we were looking at an input that was only 1 rad per second. I picked here just kind of for no other reason of going from minus 2,000 to 2,000. You might find that that's too big of a range. You might need to go smaller, or you might not get enough information out of that. So this particular line might get adjustable. We'll talk about that later. You're going to probably have to adjust those frequencies to cover a range that hits the important kind of detail of the system. So I would recommend, as you go through this, do this in an M file, right? And then play with some different values. If you make it a bunch bigger and you aren't seeing anything else going on, right? Drag it back a little bit just so you can focus on the area where action is happening. If you do it and you make it bigger and you see all sorts of new detail, well, keep making it bigger until you can see everything that you need to see. Now I'm going to make two subplots. I'm going to go ahead and take the first subplot and I'm going to plot the frequency variable against what? The absolute value. So this is going to be magnitude response of h evaluated when s equals what? J times omega. That's it. So that gives me magnitude response. Switch over subplots and do the same thing for the phase. So plot out the frequency variable against the angle of h, substituting s for j omega. So this guy is phase response. This guy is magnitude response. Very easy to do. Set up an anonymous function. Set up your frequency variable, and then direct substitute. We have already made the comment here, right, that you might have to adjust the range of omega depending on whether you did a good job of guessing to begin with, right? And you probably want to label axes and all that sort of stuff just so it's a readable graph. Next time, we will do several examples, some pretty simple examples to begin with, of carrying out frequency response ideas on some common systems. And then we are going to look at estimating or coming up with approximations or being able to sketch out both magnitude and phase response using pole zero information. I will emphasize the role of poles and zeros in system behavior. That'll all come up next time.